Hey everyone, I'm Anish and welcome to PrepFusion. So today we will be starting the lecture 2 of my Routh stability criterion chapter, right? So before starting this lecture, I will go to the previous question because I gave you a homework, right? Few homeworks for assignment questions. So that we will do. So this was the assignment, right? We have to compute the Routh table for the following and check for stability if these polynomials are okay, if this polynomials, check for stability if the polynomials are characteristics equation of the CLTF. So this should be the, not this, these are the characteristics equation of my CLTF. So firstly I will take this polynomial and compute the Routh table. So let me take this one. Okay, so if I take this one, what do I get? I get this one like this one, right? As this is like, I will first write the columns, right, of all the powers of S. So this will be s cube s to the power 1 s to the power 0. Okay, s to the power 0. So that is what that will take. Now what I'll do, I'll write the first two rows, right? I'll write the first two rows. So the first will be 1, then I will skip this coefficient, I will take this coefficient which is 3. Okay, and like I can take the other coefficient also, but it will be null, right? Because after this 3 I have to skip this one. After this, what is there? It is 0, right? So I will take 0, but anyways this won't come in handy because this whole column will be 0 anyways. So now the second row, I will take this coefficient which is 1 and this coefficient which is again 1. Okay, 1 and 1, and this is 0. Okay, and now I have to start my computation, right? So what do I do for computation? Basically first I multiply this one with this one and subtract this one with this one and then divide by this, right? So let me write this with some other colors. Then this is this one color, this is, let's say, this color, and this is, let's say, some different color, right? Yellow. So I will write it according to that. So I multiply 1 times 3, okay, then subtract 1 times 1, then divide by 1 itself, right? So this become a bit bigger. So what I will do is I will just apply a bit of trick that I will reduce the size of this one. You can't do that, right? So that's unfortunate for you, but I can. So yeah, this will be this one. So what is the result of this one? The result of this one is basically 2, right? The result of this, okay, I need to reduce the size. Result of this one is 2. Okay, so this is the this column. Now let's go for another column, right? Let's go for another column. So what is my another column telling me? So now what will be the next next column, basically next element? So now I will choose this column, right? And this is null, this is 0 basically. So again, anyways, I'll get 0. But if you want to calculate, you can calculate 1 times 0 is 0, then subtract 0 times 1 is 0, then divide by 1, which is 0 itself. So we'll get 0 for the next column, right? Okay, then I don't solve. If I'm getting the this and this one as 0, then I won't solve for this one, right? This one will also come 0. Okay, so yeah, I stop there. Okay, so because this row is 0 anyways, I can see, so there is nothing after this. So if I choose this one, I have to choose something here, right? This is null, this is 0, that's why I don't go after this. Okay, so it may so be non-zero, but something has to be present over here, right? Something has to be present over here, then only I can calculate, right? But this is 0, that's why I stop here only. Okay, now for the last row, I have 2 here. Then this, what is the trick that I told you? I have a 0 in this element, right? So if I have a 0 around this, right, then this simply will come over here. Okay, but let's verify. So this is 2. Okay, so 2 times 1. Okay, so now I will delete this actually because this is like coming in between my multiplication, so you will not understand. So what I'll do, I will put this 2 over here. Okay, now what I should do, I should multiply 2 into 1 minus 1 into 0 divided by 2 itself. So what do I see? 2 into 1 is 2 minus 0 divided by 2. So I get as 1 itself, right? This one will come here, 1 itself. So this is 1. So okay, so this is my 1. Okay, so how many number of sign changes do I see? So what I see is, this is first row is plus, okay, first row is positive element, second row is positive, third row is positive, fourth row is also positive. So is there any sign change? There is no sign change. No sign change. What does this mean? This means that there is no poles on the right half plane of the S plane, geometry axis. So no poles on the right half plane of j omega axis. Okay, j omega axis. So yeah, the first case is done. As we solved from the this computer calculators also, the found out the roots. From there also we saw that I had two complex conjugate roots which were on the left hand side and one real negative root, right, which is also on the left hand side. So this is also, we can cross verify, right? Yeah, this is giving the correct answer. Now let's go for the second option, like the part B. Okay, this one. So what is my part B? So part B, right, again I will compute the Routh table. So what I will do is, this will take me a bit of time. This is s cube s square s to the power 1 s to the power 0. Okay, again I compute the Routh table. Now I write the coefficients, right? First two rows, this is 1 comma 1, this is 1 comma 3, and these are 0, right? These are 0. Now what do you do? Basically, right, now we multiply 1 times 1, subtract 1 times 3, right? So this is minus 2 divided by 1 basically, so I get minus 2. So now I will do this fast, right? So first example I went very slow. What was it? It was 1 times 1 minus 1 times 3, minus 2 divided by this one element, right? So I get minus 2 over here. Now again this is 0, right? 0, so this will come out to be 0. So if my column is 0, like in this element, if I see 0 here, right, for this element, it will be simply 0 because everything is getting multiplied by 0 itself. So again it will be 0. Okay, again I can apply the trick that my 3 will directly come over here, right, as my 0 is present over here. Okay, but this above element is not 0. If this above element was also 0, then I would have got a 0 over here. Okay, so but let's calculate. So this is minus 2 times 3 minus 1 times 0, which is 0, divided by minus 2. So I get 3 itself, right? So this is 3 itself, and the next elements are 0. Okay, why? Because the elements after in this column, right, are nullity, right? 0. That's why I get 0 over here. I get 0 over here. Now what do I see? I see that I have a negative number. So this is interesting. So let's write the signs of each rows, right, of the first column. So this is positive, then this is positive, this is negative, okay, and this is positive. So these are my signs. Now what do I see? How many sign changes do I have? I have 1. Is it? No, right? I have 2, right? Why? Because from s cube to s square I am going, no sign change. From s square to s to the power 1 I am going, there is 1 sign change. From s to the power 1 to s to the power 0 I am going, there is again another sign change. Why? This is going from plus to minus and this is going from minus to plus. So how many number of sign changes I have? Number of sign changes equals to 2. Okay, I have 2 sign changes. What are these? One is from s square to s to the power 1, okay, and another one is from s to the power 1 to s to the power 0. So these are my 2 sign changes. Okay, 2 sign changes. Now as I have 2 sign changes, I will have 2 poles on the right hand side of the s plane. So two poles on the right hand side of the j omega axis, right? Okay, we already found it out from the previous example, solved it in computer, and we found out that there were complex conjugate roots. So hence we know that this is already unstable. So that means unstable, right? Unstable system. Okay. So yeah, from here we can understand, right, if my roots lie on the left hand side or the right hand side with the help of sign changes. So we cross verify, right? We cross verify. Now I have, like, this is the third order equation, and what I can understand that two poles are on the right hand side. Can I comment about the remaining pole? Can I comment about that pole? Let's see. Firstly, will it be on the will it be on the imaginary axis, or will it be on the complex? Will it be complex conjugate? Basically, it can't be complex conjugate. It will either lie on the imaginary axis or on the real axis, right? Real axis negative. Why can't it be complex conjugate? Because I need two poles, right? And all these are real coefficient, and I will, for complex conjugate roots, I will need on the left hand side, basically on the left hand side for complex conjugate root I will need two poles, but I have only one remaining pole that I need to decide where it is residing, right? So complex conjugate is gone, right? That option is gone because I need two poles for that. And if I have a complex pole, right, for this equation, if I have a complex pole, there will always be a conjugate one. Okay, there will always be conjugate. Why? Because the coefficient of all these are real, so they will all, the complex poles will always present in conjugate form. So complex conjugate is gone. Now will they lie on the imaginary axis? Okay, on the imaginary axis or on the real axis? Okay, on the left hand side. Right hand side it is not possible. On the left hand side will they lie? So this, right, this will discuss in some special case of this Routh array itself, which is known as the row of zeros. From there we will understand. So yeah, just wanted to give you a bit of hint that what about the other pole. Okay, just for a bit of thought, right? What about the other pole? So that will lie either on the left hand side, the real axis of the left hand side, or on the imaginary axis, right? One of them. Okay, one of them. So like an imaginary axis, right? Imaginary axis, again they will have to lie in the conjugate form. So if one is in j minus 2, another one will be in plus j2. Okay, but I have only one pole left, so again they can't be in conjugate form. So what is the other option? Imaginary axis. What is the other option if only one pole is left? Only it can lie in the origin, right? Origin has only, like, it can lie one pole. So but if for my pole to lie on the origin, what is needed? The constant term should be 0. This constant term should be 0. Is it 0 here? No, it isn't 0, right? Hence that thing is gone. That 0 is not a solution. Hence my pole will lie on the left hand side of the g omega axis. So like this you can evaluate for the remaining pole, where will the pole lie. Okay, so like let me write this down, that what about the remaining pole. Okay, so what can happen? Three things can happen. Either on the negative real axis, or what other thing can happen? Or they can be in left hand side but in complex conjugate form. So left hand side but in complex conjugate, or they can lie on the imaginary axis, but imaginary axis has also two imaginary axis, but also has like two conditions. One is at 0, okay, s equal to 0, and what is the another one? Another one is basically conjugate imaginary roots, right? Conjugate imaginary. So conjugate imaginary. So what is the requirement? This will need only one pole is sufficient, right? One pole is sufficient, but this will need two poles, right? It is in complex conjugate form, so this will need two poles, which is I have only one remaining pole, right? One remaining pole. So this will need two poles. Hence this I will eliminate. Now here, right, I have only one pole requirement, one pole. Okay, but this will give me only one solution, one pole. So this can be okay. So I should write here can be. So can be, right, can be, and here also I can write can be. But this again, right, this conjugate imaginary, right, will again give me two poles. So this can't be two poles, it will give. Okay, so that this can't be giving me the solution. So these two can be, but again this s equal to 0 is eliminated. Why? Because let me take another pen. Eliminated because constant term is not equal to 0. Hence this is my solution, final solution. Hence what can I say? That I will have two poles on the right hand side, and I will have one pole on the left hand side on the real axis, on the real axis. Okay, so this is the complete solution of this Routh array, right? Now let's solve for the third one. Okay, what was the third one? Third one was okay, third one was special case. Why? Because I wanted to like tell you why I told you one key point, right? Why did I say so? So let's see. So let's take the third polynomial and compute the Routh table, right? So if I compute the Routh table, what do I see? So again, right, I will write here s square s to the power 1 s to the power 0. Okay, and what is this? This is a naught. Okay, I will write the first row, and again I will skip one. This will be a2, and this will be a1, and this will be 0. Okay, again I will do the simple calculation. What will this will be a1 times, okay, what will happen? This is a shortcut, right? Here I have 0 beside this, so this a2 will simply come over here, right? So this will be a2. Okay, so for my system to be stable, or for no pole to lie on the right hand side of the S plane, what needs to happen here? What needs to happen? My E naught, like I need to have a positive sign, right? All of them, either positive or negative sign, same sign. So my E naught, E1 and E2 firstly should be non-zero, because that is also another condition. Okay, not equal to 0 should be non-zero and of same sign. Same sign, right? Should be non-zero and of same sign. Okay, so from here, as I told you, right, I wrote that point that from the Routh table I can clearly understand that I don't need to compute the Routh table. I can just say from all the coefficients that they need to be either same sign, all of them should be same sign, and they should be non-zero, they should not be 0. That is the sufficient condition that I applied here, and the sufficient condition becomes a necessary basically necessary condition becomes a sufficient condition only, right, for a second order polynomial or a lower order also. So as I wrote here, right, let's see, where did I wrote it? Yeah, this one, right? The necessary condition becomes sufficient. What happens for polynomials of any order? A necessary condition for them to be Hurwitz is that all coefficient must be non-zero and same sign. That is what it is telling, right? That is what my computation is telling. So what I can write over here is, hence my necessary condition becomes, my necessary condition becomes sufficient for like second order and lower order polynomials. For below third order polynomials. Okay, so yeah, this was it for this all this homework assignments. Now let's start our actual topic of the lecture, right? Okay, so what is this lecture about? This lecture is about basically the special cases of Routh stability criterion, right? We learned that if the first column, if there are zero number of sign changes, then my system will be stable. But if in the first column there is a 0, then what do you say? What I told you, right, that the first column should be non-zero. But if my first column is 0, then what do I say? I mean, then what do you say about the poles, right? Will they lie on the right hand side of the j omega axis, or will they be on the j omega axis itself? So system will be unstable, that we know. If the first column is getting 0, system will be unstable, that we know. But we also want to know about the location of the zeros. Are they imaginary or they are lying on the right hand side of the S-plane? So that we'll understand. Also, if the whole row becomes 0, then what happens? If basically one column in the column, one of the element becomes 0, first column, then I told you that we'll see. And if the whole row of a particular row, right, it becomes 0, then what happens? We'll see, right? So we'll have two cases. So what is the case 1? Case 1 is the first element in any row of the Routh's array is 0, or you can say the first column has any of its elements 0, equals to 0, with the other elements being non-zero. Basically the first row, okay, first element is 0 and other elements is non-zero. Okay, other elements is non-zero and only the first row is 0. Okay, so what we'll do, basically, right, we will replace this 0 with a dummy variable known as epsilon. So we will replace zero dummy variable epsilon. Okay, this is known as the Greek letter epsilon. So please epsilon. Excuse my spelling if my spelling is wrong. Okay, I think this is spelling, it should be SIEPSI, so whatever this is. So now, right, as why do I have to do it? Because if you see, like, let me do an example. Let's say in my router I have 1, 2, then 0, then this 1. What will happen if this is 0? If this is 0, I will multiply 0 times 2, then subtract 1 minus 1 and then divide by 0. So this row, right, this one will become infinity. Okay, this one will become infinity, which is obviously we can continue with that, right? So what we do, we replace this 0 with the epsilon and then further continue, because this will terminate my computation of the Routh array. Okay, that's why we do this. So that's why we do, and we continue our computation of the Routh array with epsilon, and we assume that epsilon is a small positive real number. Okay, so we assume epsilon is a small real number. Okay, so epsilon is a small real number, and we continue further. Okay, and we continue our computation. Okay, and we continue our computation. Okay, so yeah, here what is written, the Routh table, like this is the reasoning, right? The Routh table will terminate immediately. To extend the Routh table, we'll replace that 0 with variable epsilon. Okay, epsilon will replace, and then we will again restart our computation of the Routh table. Okay, not the root, it's the Routh table, sorry. So this will be Routh table. Okay, now after completion of the Routh table, again what we will do, we will again replace that variable with 0 in the first column of the Routh table. So after all the computations has been done, then we'll replace my epsilon equals to 0, and then we'll see what are the signs of the first column of each element, right? That we'll see. Okay, once we do one question, there we'll understand. So this is what we do. So now it will tell us what happens if there is sign change. So let's read this statement first. If there is a sign change from the entry above epsilon in the first column of the Routh array to the entry below, sorry, this should not be B, this should be below epsilon, then there are roots in the right half plane, right? So if there is a sign change from the entry above epsilon in the first column of the Routh array to the entry below epsilon, then there are roots in the right half plane. Okay, we know like this is basically deciding between will the roots be in the right half plane or in the j omega axis. Let's see. So what does this mean? So I have this epsilon here, right, and above this there are, let's say, 2 rows which are 1 comma minus 1. Okay, and there are again 2 rows below this epsilon. So let's say I have s to the power 4 as the highest power. So this is again, let's say 1 1, right, 1 1. Now what does this tell us? If there is a sign change from the entry above epsilon in the first column of the Routh array to the entry below epsilon, then there are roots in the right half plane. So what I can see, there is a sign change, right? There is a sign change, so there will be poles in the right half plane. Now if here was also there sign change, then here also I can say, yeah, there will be poles on the right half plane. Okay, so from here I can understand. Now what is the second condition telling? If not, then there is a pair of roots on the j omega axis. So if there isn't any sign change, right, let's say there isn't any sign change, all of these are positive. Okay, then what I can say is that my location of poles will lie on the imaginary axis. There will be pair of roots which will lie on the imaginary axis. So this is what this case basically explains. Once we do few more questions from there, we'll understand. Okay, so this is the basically question. So we have been given that we have to compute the Routh table and check the stability of the system if the characteristics equation is given below, right? We have been given the characteristics equation, the two of them. We have to compute the Routh table and check the stability of the system. So let's first check this one. Okay, let's first check this one. So we'll copy this one. So I check this one. So what did I see? So this, right, now I will just write down the coefficients and all those things. So this will be s to the power 5, s to the power 4, s cube, s square, s to the power 1, s to the power 0. Okay, and what do I see? And so let me write down the rows, basically first 2 rows, right? So first row is 1, then I skip, and then I write 2, then I skip again, I write 3, and I skip. So this will be 0. So I will not write it here, right? So why, we will see, because this is 1, then I skip 1, this is 2, then I skip this one, I take this one, and here I have nothing, right? So yeah, this characteristic equation should be equal to 0. That is my characteristic equation basically. So this is 1 2 3. Now what is this one? I will take this one because I will took this one for the first row. So this will be 1. Okay, then this is 2, and this is 15. So 1 2 15, and this is completing my Routh array, right? I don't need to take extra elements. These are 0 anyways. So if you put 0 here, it won't matter. If you don't put anything, that also won't matter, because these are not getting used. This is the maximum point, right, that I've reached. Okay, the last coefficient basically. So yeah, we stop here only, right? So if my last coefficient was here, then I would have taken a 0 over here. Okay, yeah. So now let's compute the Routh array basically. So what do? I multiply 1 times 2 and then subtract 1 times 2 and divide by 1. What do I see? I get a 0, right? I get a 0. So if I get a 0, what I'll do? I will simply write here, I write 0 over here, then I will simply replace this 0 with epsilon, right? Now I will compute further now. Okay, because if there is 0 here, I can't compute here, right? That is an issue. That's why I will just compute this using epsilon. Now what is this term? So this is equals to 1 times 3 minus 1 times 15, that is minus 12 divided by 1. So this is minus 12 and this is basically 0. This is 0, right? This is 0. Now I compute this one. So if I took 0, what happened? I multiplied 0 with 2 and subtract with 1 minus 12. So minus plus 12 divided by 0. So it blows up, right? Blows up. So I won't be able to do that. So what I'll do, I will write epsilon. So this is epsilon, 2 epsilon. So this is 2 times epsilon and then plus 12 divided by epsilon itself. Plus 12 divided by epsilon. Okay. So I have space over here. Now calculating this one will be difficult. What will come over here? This is 0, right? Beside this is 0. So what will come over here? Tell me. This will be 15, right? 15 will directly come over here. Shortcut, right? So I don't need to compute further. So if you want to, you can compute and you will see 15 will come over here. Okay. And this will be 0 itself. Now what will come over here? This is a task. This is a calculative task because this is multiplied with this one and this is multiplied with this one, then subtracted by this one. So this is a task. So I will solve this separately. So basically what I do, I multiply 2 epsilon plus 12 divided by epsilon into minus 12 and this is minus epsilon to 15, right? Minus epsilon to 15. Okay. And then divide by then what you do, then divide by this one itself. So what do I get? I get this one as basically this will be divided with this one. So I will get only minus 12 and this is what? This is minus, so this will go over here, epsilon square by 15 divided by 2 epsilon plus 12, right? So this is my equation. So I will just equate it like this one. What did I do? I just simply divided by this one and this one, right? So this is what I get. Epsilon I took over here. So I will just write in small, then I will put epsilon equals 0. Then we will see what happens, right? So this is here, and what is this one? This one is simply 0 because this column is basically 0, right? 0. So this I will get as 0. Okay. Now what will be this one? Again apply the shortcut, right? Don't even look at this one. This one will be directly here. Why? Because I have a 0 over here. So we get 15 over here. And this will be 0, right? Again like this, I don't need to write because this will go on to nullity, right? So now what I'll do, I will put my epsilon equals to 0. Okay, now what I'll do, I'll put my epsilon equals to 0. So if I put my epsilon equals to 0, what do I get? So if I put my epsilon equals to 0, I will put this one as 0. So if I put this one as 0, I will assume that this one is a small positive number. Okay, and like if I divide by, okay, let's say if I divide by plus 12 divided by 0, what do I get? I get almost equals to positive infinity. Okay, so I will assume my epsilon is some small positive number, right? Small positive number. So if this one I can neglect, right? 2 times a small number 0.00001, it will be 0 only, and this will be 12 will dominate. So 12 by some small positive number, what I'll get? I will get positive infinity. So this is an analogy. You think it like this one. This will be easier for you to understand. So this will be, if I put epsilon equals 0, this will be plus infinity. So this is, sign is important, plus sign. Okay, sign is important, plus sign. And if I put epsilon equals to 0 over here, what do I get? So if I put epsilon equals 0, what do I get? So epsilon equals 0, this goes to, numerator goes to 0, and this is some finite value, right? Finite value. So basically, or if you put some small positive number also, it doesn't matter. But here you can put 0. Here we simply can't put 0. That's why I chose small positive number. Here if I just simply put 0, what do I get? I get this numerator 0 and denominator is some finite number. So 0 by finite number is 0 itself. So my final result will come out to be minus 12 itself. Okay, minus 12 itself. So this I can write here. Okay, I can replace this one with minus 12. Okay, I can replace this one with minus 12, and I have minus 15 over here. Okay, plus 15 over here. So below epsilon, how many sign changes I have? Below epsilon I have 2 sign changes. Above epsilon, how many sign changes I have? 0 sign changes, right? So what I will write, above epsilon I have 2 sign changes, and this is for below epsilon. Actually, above epsilon I have 0 sign changes. I have 2 sign changes, right? So what can I interpret from this one? So I can say that my 2 roots are I have 2 roots on the right hand side of the S plane. So from this statement I can interpret I have 2 roots on the right hand side of S plane. Okay, this is what I can interpret as. So did I write this here? Okay, dummy variable epsilon, and assume small real number, and assume it as small positive. Okay, assume it as small positive, so that will only help you in calculations. So yeah, you can do this one. So like from here you can understand, right? If I have 2 sign changes, I got like 2 roots on the right hand side of the S plane. Basically this is not stable. Okay, hence this will be of S plane. Not stable system. Okay, this is not stable system. Okay, so I can like obviously say this system is not stable. Now let's do it for the second case. So let me take this one. Okay, copy this one and paste it over here, right? So if I paste it over here, now I will construct the Routh table basically. So let me construct the Routh table. Write this as s cube s square s to the power 1 s to the power 0. Now what are my coefficients basically? So my coefficients, right, 1, skip this, and 1 1. So again what I am saying, I am getting a 0 over here, right? I am getting a 0 over here. And what will be the next term? This is also 0, right? So this next term will be 1 itself. Okay, but I will replace this one with epsilon. Okay, but this is also a special case. Why is this a special case? Because here, right here, I have got a like a full row of 0 also, because this is also 0, right? So this case will be also be covered in the second case also, but still we'll use the first case. Okay, and as here I have 0, then what will happen? This one will come over here, shortcut, right? Shortcut. So this one will come over here, right? Now this I have replaced with epsilon. So how many number of sign changes I have above and below my epsilon? So again I will copy this one, so directly I can see, right? Okay, let me write the sign changes here, right? So this is basically positive. This I won't compute. This is positive, this is negative, right? So here I have one sign change from s to the power 1 to s to the power 0. Okay, so here I have one sign change. Okay, so yeah, now let's do it for, I just wrote it this one for the further simplification. So let's copy this one. okay, and I will change the statements. So yeah, I don't have space, I will add another page. So what do I see? Let me write the signs, right? So this is plus, this is plus. I won't write the sign of this one, okay, I will write the sign of this one, plus. So what do I see? There is no sign change, right? No sign change, no sign change, okay, there is no sign change, right? So yeah, this is basically my polynomial. This should be equal to 0, okay. So if there is no sign change, what does that mean? As I told you in the key point, right, in the rule, that if there is no sign change, then there will be pair of roots which will lie in the j omega axis. So I should write here is, I have no sign changes above and I have no sign changes below also, okay. So I will have roots on the complex conjugate roots on the imaginary axis. Okay, conjugate roots on the imaginary axis basically. So yeah, this is basically what this is. So now, right, what can I say about the other root? So other root obviously won't be on the right hand side because I have no sign changes. So can it be in the origin? It can't be in the origin, right? I have a constant term, so it will be on the left hand side. So I will have one root on the left hand side and other roots will be on the imaginary axis. So like this is a very famous equation, okay. So if you understand, this is plus j, okay, you can understand this is like a imaginary component. The solution of this one is plus minus j, okay. So if you put plus j over here, what will this become? So this is a famous equation. So if you know, right, the solution of this one is s equals to plus minus j. This is what this one is telling, right? So if you put s equals to plus j, so let me write it down so you will understand. So this will be plus j whole cube plus j whole square plus then minus j then plus 1, which is equals to what? So what is j cube equals to? J cube, right? J square is minus 1 and times j basically is a complex number, right? So j square is minus 1, I hope you know. Then times j is minus j, so j cube is minus j, so this you should know anyways. And then j square is minus 1, okay, and minus j is minus j and plus 1. So what do you see? Okay, what am I doing wrong? Oh, sorry, I should have put plus j over here. Sorry, this is plus j, right? I put plus j in the equation. Sorry, I put plus j in the equation instead of minus j. Sorry. So this will be plus j, right? This will be plus j. So what do I get? I see j plus j and minus j cancelling each other out, and minus 1 and plus 1 cancelling each other out. This will be 0 only. This will be 0 only. So I get 0 over here, right? I get 0 over here. Okay. So yeah. So this is satisfying, and minus j will also satisfy. They will lie in the basically conjugate form, right? So what will be my other root? So what I can do, okay, I can check that I can take. So what is the equation for this one? It is what are the factors? S plus j into s minus j. So this is equals to s square plus 1, basically s square plus 1. Okay. So now, right now, if this is equals to s square plus 1, so what does this happen? So can I take any term common, s square plus 1 over here? So I can. How? So what I should do is take this, copy this one, delete this one. I can rewrite this one as like this one, right? So this is equals to, simply I can take s common over here. This will be s square plus 1. Sorry, I can take s square common over here. S square, not this one. S square common over here. This will be s plus 1 plus s plus 1. Now what I can do? I can do s plus 1 common, right? So if I take s plus 1 common, what do I see? This becomes s square plus 1, okay, and this is equals to 0. So my factors will be, one will be equals to s square plus 1 equals to 0, and another will be s plus 1 equals to 0. So from this one I can understand that I have two factors, s square equals to minus 1 and s equals to minus 1, okay. two factors, right, to this one. So this is giving me what solution this is giving. This is giving me plus minus j, okay, and this is giving me -1. This is just to show you, this is not for anything else, right? This will not come in exam. Just to show you that yes, the hypothesis that we thought that my pole will lie on the left hand side of the S plane, it is lying on the left hand side. Okay, this is true, right? So like as there are no sign changes, it won't lie on the right hand side and it won't lie on the imaginary axis, because I have only one pole left, and if it has to lie in the complex conjugate plane or on the imaginary axis, it should be in pairs, but I have only one pole left, so it will lie on the negative real axis, and that is exactly what we're getting. Okay, there is also another method to find the roots, right, factors basically. So we know this right, we know this, that plus minus j, this is just for this, we know. Okay, this don't worry, this you don't have to know, this is just for teaching you guys, okay, to make you understand that my hypothesis is true. So there is another method known as the long division method, okay, to find out the other roots. If we know two roots, to find out the other roots, long division method. So what do you do? So in long division method, basically what do you do? We know the, I forgot what we call exactly this one. So I hope you know that this is the factor, right? This what do you say? This, what is factor? This s square plus 1 is the factor. So s square plus 1 is the factor. So s square plus 1 is the factor. Okay, s square plus 1 is the factor, and what is my actual like characteristic equation? It is s square s cube, let me write in different pen, s cube plus s square plus s plus 1. okay, this is my actual characteristic equation, right? So now I will divide this with this one and I will find my quotient basically. Okay, quotient. So yeah, not quotient, sorry, I think remainder, it is called as remainder. Okay, and that will be my factor. Okay, I forgot the names, please like forgive me for the names, right? I don't remember the names exactly. So what we divide, divisor, all those things we name, right? Quotient, divisor, remainder, all those things. So this is my dividend, I think I've forgotten. So now I will divide it this one. So how I will divide this? I will try to equate the coefficient of this highest power term and whatever is present over here. So s square is present over here. What is the coefficient? It is 1, and here also it is 1. So I will multiply 1 with this one. So I will multiply 1 with this one. So if I multiply 1, so I will write 1 over here, and I will put my coefficients like this one, s, and I will put it below the powers which are equal, right? So this is s square and this is 1. So I hope you understand that in division this sign changes, we subtract with this one. So what am I left with? S cube plus s. I am left with s cube plus s. Now what can I do? I have to equate the highest power coefficient, okay, with this one. Or like, okay, sorry, one thing I forgot to do is, one thing I did wrong. Okay, like we don't do it like this one, sorry. We do what was, basically I equate the highest power of this one with this one and multiply whatever I have, right? So how do I equate the highest power with this one? So I have to multiply s, right? If I multiply s with this one, I will get s cube. So here the coefficient is 1, so I will multiply just a 1 times s cube, 1 times s, right? So if I multiply s with this one, what do I get? I get s cube over here and I get s over here, right? S times s square plus 1 is s cube and s. Now this is simple division, so I will subtract this one. So what I am left with, this is going to cancel out. That is my main motto, to cancel the highest power terms, and slowly I will cancel the other terms also to get my remainder as 0, right? So basically this will come out to be s square minus again this is again going to 0, right? This is again going to 0, so I will be left with s square plus 1, right? Now what I will do, I have to equate the highest powers, they are same, right? I will simply multiply 1, so I will add 1 over here. So don't worry, I will, after ending this class, I will write the names of each of these, right? What are these called, what is this called, and what is this called? So I forgotten it, I will just write it. Okay, so this is s square plus 1, so I'll just simply multiply 1 over here. So this will be again s square plus 1, and we are subtracting, right? We are subtracting. So what do I get? So this is simply minus and this is simply minus. Okay, so what do I get? This is again 0 remainder I'm getting, and this is my factor. Okay, so this is my factor basically. So if this is basically s equals to minus 1, okay, as we found it out from here also. So you can do it like this one also. Okay, so yeah, I think that's it for the solution of this one. This one has already gone long. So now we'll do the second basically case, which is the special case, which is the row of 0, also known as the ROZ. ROZ is known as the row of 0, right? So in this case, right, in this case, what will happen? All the elements in any row of the Routh array are 0. Okay, so all the elements in any row of the Routh array are 0. So what does this mean? So let's say I have like rows like this one, 1 2 3 1 1 4. Now this row, right, obviously this is just example, this whole row will be 0. Okay, this whole row will, that means this is a row of 0. Okay, not perfect calculation, I'm just telling you the example. So if this whole row is 0, then I will have a row of 0, right? I will have a row of 0. Okay, so basically, right, what happens when I get a row of 0? When I get a row of 0, I get my roots will be, what I get to know is my roots will be radially opposite. So if I have a row of 0, my roots will be radially opposite. Okay, so that is basically what row of 0 means. And what is radially opposite means radially opposite means that roots are symmetrical about origin. Roots are symmetrical about origin. Okay, so this is what basically my radially opposite roots mean. Okay, so yeah, there's this one. Then like we have few more points to explain. Okay, so what is this point telling us? Then we'll form an auxiliary equation and replace the 0 coefficient by coefficient of the differential auxiliary equation. What does this mean? What does this mean? So the auxiliary equation, okay, so like if I've got a row of 0, then obviously I can't compute further, right? I can't compute further, so I have to form an auxiliary equation. So the auxiliary equation will be the equation formed by the row above. Okay, so auxiliary equation, row above the ROZ, row of 0. Okay, auxiliary equation is the row above the row of zeros, right? That is my auxiliary equation. Once we solve a question, there we will understand, right? There we will understand. So now, right, so that row of 0, the coefficients will be formed using the auxiliary equation. We'll replace the 0 coefficient by the coefficient of the differential auxiliary equation. What do we mean by all this? Will, once you solve a question, we'll understand. Okay, and the roots of the auxiliary equation are also the roots of the characteristics equation. This also, once we solve, we'll understand. If you don't understand, don't worry, no worry, just keep this in your mind. Okay, Anish has said this, so this will come in handy at later stage. Okay, now let's draw a few radially opposite roots. What do you mean by radially opposite? So radially opposite, right, this is my sigma plus j omega plane, right? S plane. Sigma and j omega, right? So this is my sigma and j omega. What do I get? Basically, right, basically, let's say if my roots are at, one of the root is at -2. Okay, one of the root is at -2. Then where will my other root lie? To lie at +2. Okay, so if one of my root is at -2, then the other root will lie at +2. Okay, now what if one of my root is at +2j, right? +2j. So what if one of my root is at +2j? Okay, +2j. What if one of my root is at +2j? Okay, and now, right, where will my other root? So if they are symmetrical about origin, so what does this mean? This means they are symmetrical about origin. So you might say this is just like conjugate. No, there will be difference. I will tell you, right? So this is let me write it this pen. Symmetric about origin. Okay, this is symmetric about origin. So if this is symmetric about origin, what does this mean? So then I will have another root which will lie at the minus 2j. So this will lie around here, minus j2, right? Lie around here. Okay, now if this lies around here, now I will take another example. So let me take another example. So let's say I am taking 2 plus 2j, right? 2 plus 2j. Now where will my other root lie? So 2 plus 2j means I am here, right? 2 plus 2j. Okay, 2 plus 2j. Now where will my other root lie? So it will be symmetrical around this, or what does radially mean? It will be around this circle only. Circle, okay. So this is the radius of my circle from origin. So it will just be at the opposite, okay. Complete the diameter up here, right? Not here. It is not conjugate. It will lie. If you complete the circle and if I complete the diameter through the origin, what do I see? The other point will be here. And what is the location of this point? The location of this point is minus 2 minus 2j. So all of the signs will change. So what will be the location of my point? It will be minus 2 minus 2j. Okay, so this is basically location of my point, minus 2j. Okay, so I hope you got your answer, that this will be around here. Okay, so now what is the thing with this one? So like if I have a row of 0, I will get readily opposite roots. So if I found out a root is here, then definitely there will be one root here. There will be one root here. Okay, that I got to know. Okay, if I have a root here, then one root will be here. If I have a root here, then one root will be here. And if I have a root at this location, then one root will be at this location. That point I know. Now what is the other point? The other point is basically if I have a root here, then as my coefficients of my polynomial are all real, as we know that complex root doesn't stay by itself, it doesn't stay alone, it doesn't like to stay alone, right? It likes to stay with a pair. So complex root always comes with pair, which is the complex conjugate pair. So if I know I have a root here, then I must have a root at 2 minus 2j. Okay, so I will write this point as all my coefficients of polynomial are real, hence I will always get complex conjugate roots. I will always have complex conjugate roots, right? Conjugate roots. So if I get a complex conjugate roots, then what does that mean? That means if I have a root here, that is if one root is at 2 plus 2j, then my other root will be at basically conjugate of this one, which is 2 minus j2, right? And also I know due to this radially opposite property, what do I know? Basically this will be also minus 2 minus 2j, minus 2 minus 2j, and this will be minus 2 plus 2j, because these are complex conjugate. Okay, so yeah, I will have 4 roots. So if I have a complex root for row of 0, then they will come in as multiple of 4 roots. So I will find out 4 roots from just one root, right? Okay, so what does this mean? So radially opposite root can either come with a pair, multiple of 2 roots or 4 roots, right? So that is the basically conclusion of this point, that if I have a row of 0, that row of 0 can cause radially opposite roots, and that radially opposite roots can have pair of roots or can have 4 roots, right? So can have either can either can either occur as multiple of 2 roots or multiple of 4 roots, right? 4 roots. When will 4 roots occur? 4 roots will occur when both real and imaginary component present. Okay, both real and imaginary component present. Okay, so this one will happen, and when I have only the real component or only the imaginary, then I will get two roots, because they will be radially opposite. So this is the case for only real or only imaginary. Okay, only real or only imaginary. Okay, so this is the case. Now what we'll do, we'll solve few questions. So first, like I told you the theory, right? So you try to solve it, okay, but you will not be able to, because you don't know the auxiliary equation. So I will solve one question, first question, and second question you solve it by yourself. Okay, so yeah, let's solve this question. Okay, so let me take the first question and compute this one, right? So we have to compute the Routh table and check the stability of the system. So obviously we know there will be row of 0, that's why like we are studying topic, so that we know. Okay, but still let us compute. So yeah, now let me write the obviously the Routh table. So first obviously I will what I will do, I will write the rows of the S, right, from highest to lowest. S to the power 5, S to the power 4, S to the power cube, S1, S to the power 0. Okay, so what I will do, I will just reduce the size of this one a bit, because like this will take this will need size. Okay, and this one I will put it down over here, right, and this one I will put it down. I will check accordingly where my row of 0 comes, and I will make the size bigger. Okay, and like that is the advantage of mine, because I have a like tab like this one, but you have to write it in paper, which will be difficult. So why it will be difficult, we'll see, right? So now basically let me write the first 2 rows, right? First 2 rows. So if I write the first 2 rows, this is 1, this is 6, and this is 12, and this is 8, right? So I have 4 coefficients this time. So I will come at least at this point, at least at this point. So I have 3 over here, then 12, then 12, then 0, right? I don't have, so I took this one, so I will skip this one. I will take 3, 12, 12, and then 0. I don't have anything, 0, right? So now what will happen? So this is 3 times 6 minus 12, which is 18 minus 12, 6 divided by 3, which is 2, right? And then what do I do? I choose this row and this this column and this column. This is 3 times 12 minus 12, right? This is 36 minus 12, which is 24. 24 divided by 3, which is 8, which is equals to 8. And this is basically shortcut, right? I want to write here, so this element is 0, So simply I'll put this 8 over here. So this will be 8, right? This will be 8. Okay, shortcut, but you can calculate and you will find the same result. How? 3 times 8 minus 1 times 0, 0 divided by 3 itself. So this is 8 itself, right? 8 itself. This is 0. Okay. So now what do you do? This is 2 times 12 minus 3 times 8, which is 24. Sorry, 0 basically. This is 24 minus 24, 0. Okay, then I get 0 over here. I get 0 over here. Now, if I multiply 2 times 12, again 24, again I get 24. So again I will get 0, right? Again this one will also be 0 because this column is 0, so this will be 0 anyways. Okay, so I get a row of 0 over here, right? Row of 0. So now what will happen? So basically, right, I will write another row or I will delete this row, right? So I have to form an auxiliary equation. Okay, so form an auxiliary equation. So as I mentioned in that point, right, my auxiliary equation will be the row above this one. Okay, how? Let's see. So the coefficient of auxiliary equation are this one, and my highest power will be s to the power 4. Okay, so my auxiliary equation will always be in even, right? So it will start with s to the power 4. Then what will happen? I will just skip one power. Okay, so coefficient of s to the power 4 is 2, right? Coefficient of s to the power 4 is 2. Okay, then what is the coefficient of? I will skip one power. I will skip s cube. I will choose s square. I will choose s square, right? So if I choose s square, what is the coefficient of s square? It is 8, right? It is 8. Okay, then what is the coefficient of? I will again skip one power, that is s to the power 1. I will choose s to the power 0, and what is the coefficient of s to the power 0? It is 8 itself. So again 8 times s to the power 0. Now I will equate this with 0. No, not equate this. This will be my auxiliary equation as. I will name this polynomial as as. Okay, now what will be my coefficients of s cube, this row of 0, right? What will be my coefficients of row of 0? Basically the differential auxiliary equation will be the coefficients of s cube. So what I will do, I will just differentiate this auxiliary equation dA of ds, which will be equals to 8 s cube plus 16s plus 0, because this is a constant, right? This is a constant. So I get this one. So the coefficients of this one will be the row of 0. Okay, so this is one thing. Now from this auxiliary equation, if I equate this with 0, that will also give me the roots of the actual characteristics equation. Okay, as I wrote in one point also. Okay, or that point will complete, I don't know. So this is the first thing. So this will be my coefficients of of row of 0. So this will be coefficient of row of 0. So if this is coefficient of row of 0, then what will happen? Then basically what I can write is, if I make my a of s equals to 0, so here also this will also give me roots of characteristics equation. Okay, this will give me roots of characteristics equation. Okay, so yeah, so this is it. So now right now, if this is equals to, this is s to the power 4. So I am equating this with 0. So let me write this s square plus 8 equals to 0, and this is s to the power 4 plus this is 4s square plus 4. Now what can I do? So I know I will get radially opposite roots, right? I know I will get radially opposite roots. What can I do? I can simply put s square equals to x, right? Simply put s square equals to x. So that's how I will solve this one. So I will let x equals to s square. So after replace in this equation, it will become x square plus 4x plus 0. Okay, so this is what my auxiliary equation is. Now if I equate for x, what does it become? So simply this is basically x plus 2 whole square, right? X plus 2 whole square equals to 0. So what do I have? I have x equals to minus 2 and minus 2 repeated poles at the negative half, right? But this is what x is equals to, but I am interested in what s is equals to. So x equals to s square, so I'll replace s square equals to minus 2 minus 2. This is repeated again. Now I'll take the square root. Okay, so if I take the square root, I hope you understand that if I take negative of square root, what will I get? I get s equals to plus minus j under root 2 plus minus j under root 2, right? So this is what I get. Okay, so I have 4 roots this time, and 2 of my roots are repeated, right? So on the imaginary axis, so they are like this one. We'll do more questions and understand, but for now, like at least I got my 4 roots. So this is what is the order of this equation? It is 6, right? So out of 6 roots, I got 4 roots itself. So I'm already left with 2 roots. So we'll obviously proceed further and then we will see. Okay, so this is j omega, and I have obviously these are repeated, right? I have at location plus j root 2, I have 2 poles. So this is j root 2. So I have repeated roots over here. So again this is repeated, and at minus j root 2 I have again repeated. Okay, so this is plus j root 2 and this is minus j root 2. Okay, so yeah, this is what like the 4 roots location are like. Okay, these are at the imaginary axis itself. So like from the auxiliary equation I can find. So if you put these values, you put this value minus j root 2 in this actual equation, and you will see that yes, you are getting your equation satisfied, which is equals to 0, right? You will get 0 if you put this one. Okay, so so let me write this point. Okay, so about the auxiliary equation, that for finding the auxiliary equation, you look at the row just above row of 0. Okay, just above row of 0. So that is what you look. Okay, so that is my auxiliary equation. So we solve the auxiliary equation, and this is known as the differential auxiliary equation. Okay, differential auxiliary equation, and this is known as the auxiliary equation. Okay, so yeah, now these will be my new coefficients, right? These will be my new coefficients. So I hope you understood. So let me copy this one and again rewrite this with my new coefficients basically. So if we rewrite this with new coefficients, so what are my new coefficients? My new coefficients are this, right? 8, like s cube has 8 and it has 16. So I hope you understand that we skip one power. So s cube has 8, and my like this s to the power 1 has 16, right? S to the power 1 has 16. So it is 16. Okay, so this is again equals to 0, and now I will again restart my computation. So again I will do 8 times 8 minus 32. So 64 minus 32 is basically what? 32 itself. Then I divide by 8. So what do I get? I get 4 again, right? So next, if I multiply 8 times 8 and then subtract 2 times 16, that is basically 32, and 32 divided by 8 is 4 itself. So I get 4 here. Okay, I get 4. Then what is this? This is 0, right? So 8 will directly come over here, shortcut, right? So 8 will directly come over here. Okay, and this will be 0 basically. This will be 0. Now if I multiply 4 times 16, what do I get? I get 64. And if I multiply 8 times 8, again I get 0, right? I get 0. So I get a 0 over here. Okay, I get a 0 over here, and again this one will be 0 again, okay, because this is 0, right? So you compute this one again 0, so again, right, I get a row of 0. I get a row of 0. Again I have to form a auxiliary equation, okay, again I have to form an auxiliary equation. So if I form an auxiliary equation, what do I get? So this basically, again, right, this one was my first auxiliary equation, so let me name this as a1, and this one will be my a2 of s. a2 of s equals to 4s square plus 8, right? So it is 4s square plus 8. Now what will my row of 0 coefficients? My row of 0 coefficients will be, I will differentiate this will be dA2 ds equals to 8s plus 0, okay. So this will be my coefficients. So again I will copy this one, okay, again I will copy this one and go to new page basically, and replace this row of 0 with my new coefficients, okay. I will not take care of the roots for now. I will not take care of the roots, okay. The roots here also I can see they are plus minus 0 2, so that we'll see. Only one auxiliary equation will give me all the roots. This is just the repeated case of that one, okay. So yeah, we don't have to think about that. So I will replace the coefficients here, right? It will be 8 and 0. So let me mark this one, 8 and 0, okay, 8 and 0. Yeah, just hold on a second, I can call. Yeah, sorry for the disturbance, some call came actually. Yeah, now this is 8 0. Now this will be 8, okay, this will be 8. So like just a shortcut, right? Just 8. Now is there any sign change? Can I see any sign change? I don't see any sign change. So my other two roots will lie on the left half of the S plane, right? Left half of the S plane. So as I don't see any sign change, my other two will lie on the left half of the S plane. So this is plus 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 plus, this is 1 2 3 4 plus plus plus. So like the remaining two roots, no roots on the right of S plane, right? No roots on the right hand side of S plane, that is j omega axis, right? J omega axis. So either they will be in the complex conjugate form, or they will be repeated in the negative form, or they will lie on the imaginary axis, some other location. So that is basically it for this question. So yeah, the system is not stable, that we already know, right? Because I have got a row of 0. Row of 0 means system is unstable. So either they will lie in the imaginary axis, or they will lie in the right hand plane. So right hand plane I don't see, but I see they lie in the imaginary axis, right? So system will be unstable. So one thing, as I told you, right, that there are no roots on the right hand side of the S plane. Also I told you that my roots will lie on the left hand side, okay. They may be like complex conjugate, or they may be repeated, or they may not be repeated lying on the real axis. That may happen, right? So can I find those roots? As I told you, right, that we have a method, right, that division method. So what is that division method? That division method is basically this one, right? That I know 4 roots, right? I know 4 roots. What are the 4 roots? So 4 roots are here, right? 4 roots are here. Can I form an equation from this one? Can I form an equation? What are my factors? Okay, so I have 4 roots. So can I find my factors? Actually, one of the factors is s plus j2, then other one will be s minus j2 under root 2, that is. Then again these are repeated, right? These are repeated, so this will be square and this will be called square, right? But what I know, a plus b into a minus b is a square minus b square. So this will come out to be this whole square. I can take it over the whole bracket, right? So what I can write is, this is over the whole bracket, and what do I get? I get s square plus 2, right? I get s square plus 2, okay. So this is basically my factors, right? 4 factors. Now what I'll do, I will basically divide this one with my actual characteristics equation, and I will get my other two factors, okay. Let me do that, and then I will see, right, what happens. So we'll copy this one, and we will use the, what do you call, the long division method, right? So the long division method, what does it tell us is that basically, right, I like remember the name now, okay. I remember the name. Basically this one are the factors, okay. Let me copy this one. This is the factor, right? Now can I further simplify this one, like s square plus 2 whole square. What is this equals to? This is equals to s to the power 4 plus 4a square plus 4 itself, right? Plus 4 itself. Okay, so this is my what my equation is. So now, right, what I can do, I can write this here, that I'm dividing it by this one, s to the power 4 plus 4 square, okay, plus 4. So this is basically with which I will divide it. This is divisor basically, and here basically my quotient will come, and this is my sorry, I forgot again the name, sorry. I will just write the names, okay, please excuse me, these names are very confusing. So here whatever comes is the remainder, okay, at the end whatever comes is the remainder. That I remember, right? Okay, so now what you need to do is equate the highest power with this one, right? So this is has coefficient 1, so I have to multiply just s square with this one, right? S square. So if I multiply s square, what do I get? This is s square I multiply, so I will get s to the power 6, then this will be plus 4s to the power 4, and this will be plus 4s square. Okay, so now I will subtract this one, because I hope you know division, that is the common thing. So yeah, this will be minus, this will be minus, and this will be minus. So this is getting cancelled, this is getting 2s to the power 4 I'm remained with, and I'm remained with here as 688 s square, right? Now what does this other things will come in here? So this will be 3s to the power 5 plus 12s cube plus 12s plus 8, right? Now what I will do, now I need to equate this one, right? Equate the coefficient of this one. So what I will do, I will multiply 3s, right? 3s I will multiply. So if I multiply 3s, what do I get? So let me take a different color. So if I multiply 3s, what do I get? This will be 3s to the power 5, then I will get here plus 12s cube, and this will be plus 12s. I hope you understand, right? I'm just multiplying 3s with whole of this and then subtracting. Long division, simple long division, okay, nothing to explain here. So this will be minus, this will be minus, and this will be minus. Okay, so what do I get? This will get cancelled, that's why we did it, to cancel the first term obviously. Now what I'm remained with, this will be 2s to the power 4, this will come down, and this will also get cancelled, and this will also get cancelled. Such a satisfactory feeling, right, when everything is getting cancelled. So yeah, these are getting cancelled. So now what I am remained with is plus 8s square plus 8. Okay, so I can reduce the size a bit so that I can fit this whole thing in a page. So yeah, now what do? I multiply simply, this is 2, right? Coefficient is 2. If I simply multiply 2, I will be sorted, right? So I will simply multiply with 2. So multiplying with 2, what do I get? This is 2s to the power 4 plus 8s square plus 8, right? Now if I divide this one, okay, this will be 0, my remainder will be 0. So I have got my factor basically, this one, right? So this is my factor basically. So I will copy this one, okay, and I will factorize this to find the roots, right? Like this is the combination of 2 roots, okay, as this was the combination of 4 roots, right? Multiplication of all these 4, right? Here multiplication of all these 4, right? Now I will break this down to find my roots, right? So that's how you can find roots, right? Very interesting, right? Very interesting. So even for a 6 other polynomial you can find roots, but the condition is obviously you have to know few other information also. So this is s square plus 3s plus 2. So what are my roots from here? So if I equate this with 0, so this will be equal to 0, right? So what will be the factors? Factors will be basically, this is the sum and this is the product. So it is s plus 2 into s plus 1. If you break it down, right, equals 0. So my other 2 roots are s equals to minus 2 and s equals to minus 1. Okay, s equals to minus 2 and minus 1. So this is what we understand, right? My roots here, this is proven that yes, that sign thing that I was talking about here, right, whatever I was talking about, all of them are positive, hence no root lies on the right hand side of j omega axis, they are on the left hand side, but few roots are on the j omega axis. That's why my system isn't stable. But I can see that due to this one, that this is proven that the roots are on the left hand side only. Okay, roots are on the left hand side. Also one more thing, how many ROZ do I have? How many rows of 0 do I have? This is the first, this is the second ROZ, and this is the first out of it, right? So how many repeated roots do I have? I have 2, right? Obviously x plus minus j 2 under 2, that is there. Okay, that is there. Also this is again repeated. So number of repeated roots here, what is the number of repeated roots? It is 2. So here my number of ROZ represents my number of repeated roots, right? So number, okay, I will write this one. This is also another important thing, right? So you write this one. That's why from here also you can understand how many repeated roots will I will have, right? Number of repeated roots equals to my number of ROZ. How many number of rows of zeros I have, right? Equals to my number of ROZ. Okay. So this is also another important formula, not formula, this is an important concept that you need to keep in mind. You have to keep this in mind, right? This is important. You have to keep this in mind. Okay. So yeah, this is important thing. So I think this lecture has already gone very long. Okay. So what I will do is, this one is homework for you. You do this, and in the next class we'll start from here, and we'll a bit of theory is left, very small theory is left, and then we'll start with questions. We'll only solve questions. Okay. Yeah, thank you for watching.